We presented 5 simple problems. The correct answers to all of them is A. In the game show, we swap. Married and looking, yes. Your blood test is less than 10% accurate. In Linda's profession, she is most likely a bank teller. And with the banana in the desert island, you should go with player 2, selecting 5 or 6. How did you fare? The rest of this video explains the reasoning.
The question is, should you swap? Should you stick with your original choice? Or does it make no difference what you do?
So you pick a door. What are the possibilities? You could have a goat or a car. Since the host knows where the car and the goats are, he opens a door always to show you a goat. If in the first instance you pick a goat and he shows you a goat, you know that by swapping you would get the car. Now, if you had picked the car and the host shows a goat, you know you need to stick with the original selection. Of course, the other options would always give you a goat. Now, if you know which one you picked, it's very easy. If it turned out to be a goat, you would swap. If it turned out to be a car, you would stick. But of course, you don't know that. But there is a 67% probability that you would pick a goat and only a 33% probability that you would pick a car. Therefore, because the probability of picking a goat the first time is twice as likely, you should always swap. If you recall, the scenario was Roger, who is married, is looking at Mary, and Mary is looking at David, who is unmarried. And we asked you, if a married person is looking at an unmarried person, and you had the choice of A, B, or C. In fact, most people would say we need more information, more specifically, Mary's status. As you know, Mary could be either married or unmarried, but do we really need to know? Let's take a look at this. If Mary is married, a married person is looking at an unmarried person. And if Mary is unmarried, still Roger, who is married, is looking at Mary, who is unmarried. So as you can see, it does not matter what Mary's status is. Under both scenarios, a married person is looking at an unmarried person. Now, 99% accurate means if we conduct 100 tests, 99 of the results would be trustworthy, and we would only have one false result, positive or negative. So imagine 100,000 people are tested, and we create a table. Row A is for those who have the ailments, and row B is for those who do not have the ailments. Now, we would expect 100 of these 100,000 people to have the ailments, because it is 1 in 1,000. And hence, 99,900 would not have the ailment. Now, because the test is 99% accurate, we would see 99 positive results and 1 false negative. That is, one person who actually has the ailment will be told that he does not have the ailment. Now, of the 99,900 who do not have the ailment, 1% unfortunately would be tested as false positive. That is, they would be told that they actually have the disease when they don't have the disease. And 98,901 would be told correctly that they do not have the ailments. The tests yield 1,098 positive results. However, only 99 are true positives. If you are tested positive, even with a 99% reliable test, there is only a 9.2% chance that you have these ailments. Yes, less than 10%. And the doctor wants to put you on medication.
Consider the students in your class. The number of males in the class satisfying one condition will always be greater than the number of males born in this city satisfying two conditions. Therefore, bank teller satisfying one condition will always be greater than bank teller plus music teacher satisfying two conditions.
At first glance, it may seem like player 1 has the advantage, since she'll win if any one of 4 numbers is the highest. But actually, player 2 has an approximately 56% chance of winning each match. One way to see that is to list all the possible combinations you could get by rolling 2 dice, and then count up the ones that each player wins. These are the possibilities for the yellow die. These are the possibilities for the blue die. Each cell in the chart shows a possible combination when you roll both dice. If you roll a 4 and then a 5, we'll mark a player 2 victory in this cell. A 3 and a 1 gives player 1 a victory here. Now we can see why the first glance was wrong. Even though player 1 has 4 winning numbers and player 2 only has 2, the chance of each number being the greatest is not the same. There is only a 1 in 36 chance that 1 will be the highest number, but there's an 11 in 36 chance that 6 will be the highest. So if any of these combinations are rolled, player 1 will win. And if any of these combinations are rolled, player 2 will win. Out of the 36 possible combinations, 16 give the victory to player 1, and 20 give player 2 the win.
Many real-world problems are based on data with some degree of uncertainty. Thus, we need to be cognizant of the role of probabilities in our decision-making. As Lee Iacocca pointed out, the greatest obstacle to discovery is not ignorance. It is the illusion of knowledge. Most of us believe that common sense, logic, experience, intuition, judgment, etc. can solve any problem. It is a very dangerous assumption.